In 1847, 12 miles up the Ontonagon River in what is now Upper Michigan, a mining agent named Samuel Knapp found a hemlock tree growing inside an ancient mine pit. He counted the rings, 395. The tree was nearly 400 years old. The pit was older. Knapp cleared the soil out from around the tree's roots. The pit went down 26 feet. At the bottom, beneath 4 centuries of fallen leaves, beneath layers of clay and matted vegetable matter, he found a single mass of native copper. 6 tons of it. 10 feet long, 3 feet wide, almost 2 feet thick. It had been cut free from the surrounding rock by hands that had been dust for at least 4 centuries before that tree had even begun to grow. It had been raised onto oak billets, wooden poles positioned beneath it as a cradle, so that it could be lifted to the surface. But the people who had done that work had not finished. They had left the copper there, resting on its wooden frame, halfway out of the rock, and they had not come back. So, settle in. Lower the light if there is a light. Find the position you sleep in. There is no rush tonight. The story we are about to walk through is patient. It has been waiting at the bottom of that pit for a very long time, and it is in no hurry now. If you fall asleep before we reach the end, this is what the channel is for. The pit Knapp found was not unusual. It was just the first one to be widely reported. Over the rest of the 19th century, surveyors documented more than 5,000 similar pits, some shallow, some more than 20 metres deep, running for hundreds of kilometres along the Queen Peninsula and out across the cold open water of Lake Superior to Isle Royale and beyond. The deposit they were mining was the largest concentration of pure native copper anywhere on the planet. For thousands of years, beginning, on the most recent radiocarbon evidence, at least 8,500 years ago, they took copper out of it. Tens of thousands of tons, on the higher estimates considerably more, and then mostly they stopped. Where the copper went, why they stopped, who they were answering to if they were answering to anyone at all. These are questions that have been sitting open in the academic literature for 150 years. Tonight, we are going to walk into them. The hemlock tree is long gone. Knapp counted its rings, recorded the number in a report to Congress, and then it was cut down to get at what lay underneath. But the question it had been keeping is still standing. Let's go see what it was guarding. We have to go back to Samuel Knapp because his story is even stranger than the opening described. Knapp was a mining agent for the Minnesota Mining Company, working on the south shore of Lake Superior in the late 1840s. His job was to find copper. The Quinault Peninsula had already become known as one of the richest copper regions in North America. The Jesuit missionaries who had passed through the area as far back as the 17th century had written about it. By the 1840s, a small army of prospectors and surveyors and speculators was descending on the region, hoping to make a fortune. The story of how Knapp came to find his first ancient pit is, in its actual historical detail, almost too quiet to be believable. He was not searching. He and his companion, J.B. Townsend, were trying to capture a porcupine that had taken up its winter quarters in a small cavity in a ledge of rock about 12 miles from Ontonagon. They went after the animal with a pick and a shovel. They cleared the vegetable mould and accumulated rubbish from the mouth of the cavity to flush out their game. And as the dirt came out, they realised slowly and then all at once that the cavity was not natural. It had walls. It had been cut. That is what is recorded in Whittlesey's 1862 monograph and the geological reports that followed. A hedgehog hole opened up with a shovel that turned out to be an ancient mine. Knapp went back with more tools. He cleared the pit. Below the leaf litter, below the windblown soil, he found rock that had been worked, walls that had been cut. He kept going, and eventually in 1847 at this site and at others nearby that he investigated in the same way over the following months, he found what the opening described. Pits 26 feet deep, hemlock trees nearly 400 years old growing inside them. At the bottom of one, that 6-ton copper mass still resting on its oak cradle. At the bottom of another, the same pattern, the same level of preservation, the same evidence that the people who had been working these pits had stopped mid-task, sometimes so long ago that an entire forest had grown up over what they had left behind. Knapp's announcement, made through his employer in 1848, was the first widely recognised public report of what came to be called the ancient diggings. It would not be the last. Over the next 2 years, geological surveys began to reach the region. In 1850, J.W. Foster and J.D. Whitney, 2 American geologists, submitted a report to Congress that catalogued what they had found. The list is worth reading. Their language was the dry, almost incredulous language of professional scientists who were trying very hard not to overstate what they were looking at. They described, and the wording is theirs, numerous excavations in solid rock, heaps of rubble and earth along the courses of mineral veins, the remains of copper utensils fashioned into knives and chisels, stone hammers, some of which were of immense size and weight, wooden bowls used to bale water from the mines, and one detail that matters, numerous levers of wood used in raising the masses of copper to the surface. Levers made of wood, still preserved in some cases more than 1,000 years after they had been left there, because the conditions inside the pits had kept them from rotting. The miners had floated copper masses up to the lip of the excavation using leverage and wedges. This was not a casual operation. A few years later, in the 1860s and 1870s, the larger commercial mines began to be developed. Many of the mining companies of the period, the Quincy Mining Company, the Minnesota Mining Company, later the Minong Mining Company on Isle Royale, and eventually the Calumet and Heckler Mining Company, drew, by their own published accounts, on the locations of the ancient diggings as guides to where the richest veins were. The 1875 prospectus of the Minong Mining Company devoted 11 of its pages to describing the ancient pits at the head of Macargo Cove and how the company was using them as a map. The first prospectors found some of their richest veins by following the pits that had been opened thousands of years before. The ancients had already done the exploration. The 19th century operators only had to follow, and in following, they obliterated much of the archaeological context. This is one of the great tragedies of the archaeology of the Lake Superior Copper District. The very fact that the ancient miners had been so good at finding copper meant that their pits were located on top of the best deposits. When industrial mining began, it ploughed through those sites. The 19th century operators were not archaeologists. They were not interested in preserving wooden levers or hammerstones. They were interested in pulling copper out of the ground. Much of the original archaeological context was destroyed. What survives is what survives, because someone in the 1840s or 1850s or 1860s, before the bulldozers and the steam engines arrived, happened to write it down. Letters home to mining boards, newspaper articles, drawings in mining journals, an astonishing 29-page paper by the geologist Charles Whittlesey, with maps and diagrams that compiled what was known at the time. It was published by the Smithsonian Institution in 1863 as part of the Smithsonian Contributions to Knowledge series. Whittlesey's paper is one of the foundational documents. He wrote that thousands of people had walked past the ancient depressions before Knapp's 1848 announcement without ever suspecting that they had been made by human hands. They were too shallow, too irregular, too overgrown. They looked like nothing until you started clearing them. When you cleared them, they became a record. Henry Gilman, an archaeologist and ethnologist working in the 1870s, gave an address to the American Association for the Advancement of Science at its Detroit meeting. He described in detail what had been found at one specific pit on Isle Royale, an island in the northwest corner of Lake Superior that today is a national park. In the summer of 1874, Minong Mining Company workers had cleared a pit at Macargo Cove. They had removed the accumulated debris of millennia. At the bottom, 16.5 feet down, they had encountered a mass of native copper, crescent-shaped, weighing 5,720 pounds. The mass had been worked free by ancient miners but never removed. It sat on wooden poles where they had positioned it to be raised. Around it were innumerable fragments of copper chips, and mixed in with the chips, the scales of fish. The miners had been eating during their breaks. The scales were, in Gilman's own words, evidently the remnants of the meals of the miners. Someone, thousands of years ago, had eaten lunch at the bottom of a 16-foot shaft and dropped the scales where they ate. The scales had stayed there. No one had disturbed them until the workers of the Minong Mining Company climbed down with their shovels in 1874 and found them. Gilman was asked by someone in the audience at his lecture whether there were any indications that the copper had been melted. His answer was direct. Not the least. The ancient miners had not melted their copper. They had not smelted it, and they had not cast it. They had worked the metal cold, hammering it into shape, occasionally heating it just enough to soften it for further working, a process called annealing, but never reducing it to a liquid. Cyprus and Anatolia and Mesopotamia, had been smelting copper from ore for thousands of years by the time Gilman was speaking. The world had assumed that Old World metallurgy was the original metallurgy, but Cyprus and Anatolia had to smelt. Their copper came out of the ground as ore bound to other elements, locked in compounds. It required furnaces. It required chemistry. The metallurgy of the Old World was, in part, a workaround, a sophisticated technology developed because their copper was not pure. The miners of Lake Superior did not have that problem. Their copper was already pure. It came out of the rock as metal. They did not need to invent smelting. They needed to invent a way to find it and to fracture the rock that held it. And that they had done at a scale that the more famous metallurgies of the Mediterranean would not approach for thousands of years. By the end of the 19th century, the basic facts were established. The ancient diggings extended from the Porcupine Mountains in the southwest, along the entire length of the Quinault Peninsula, and out across the cold open water to Isle Royale and beyond. A conservative survey in the early 20th century identified more than 5,000 individual pits. Later, more comprehensive surveys would put the number much higher. Some areas had hundreds of pits per square kilometre. The American archaeological establishment of the late 19th and early 20th century did not really know what to do with all of this. The standard story of human prehistory, as it was being constructed in the universities of Europe and the East Coast, was a story of Old World priority. Civilization began in Mesopotamia. Metalworking began in Anatolia. Indigenous Americans were described, condescendingly, as still in a stage of development that the Old World had passed through long before. The Lake Superior Copper District did not fit this story, so for a long time the story tried to ignore it. It could not be ignored. The pits were too many. The artefacts were too widespread. The radiocarbon dates, when they began to come in during the 1950s, were too early. The story would have to be revised. The revision is still going on. To understand who built the Lake Superior Copper District, you have to set aside almost everything you think you know about how human technology develops. The standard story goes like this. People are hunter-gatherers for a very long time. Then, somewhere around 10 or 12,000 years ago, they begin to settle down. They develop agriculture, they build villages, then towns, then cities. Specialization emerges. Some people become farmers, some become craftsmen, some become priests. Eventually, a few of those specialists figure out how to work metal. Copper first, then bronze, then iron. This usually happens in places where there are already cities, because metalworking requires resources, labour and infrastructure that hunter-gatherers can't sustain. That is the standard story. It is the story you are probably taught in school. It runs through every textbook on world prehistory. The Old Copper Complex breaks it. The Old Copper Complex, sometimes called the Old Copper Culture, is the name archaeologists give to the people who lived in the Great Lakes region during what is technically called the Late Archaic period in North American chronology. They were not a single culture in the conventional sense. There was no king, no capital, no writing system. They were a network of communities, scattered across what is today Wisconsin, Michigan, Minnesota, Ontario, parts of Manitoba and southern Quebec, who shared certain technological practices, certain trade relationships, and a way of relating to one specific material, native copper, that nobody else in the world was doing at the time. The dating has been refined, and refined again, and pushed back again. The most current peer-reviewed evidence places the oldest known copper artifact at approximately 8,500 calendar years before present. That number comes from a 2021 study led by the geologist David Pompiani and colleagues, published in the journal Radiocarbon, which re-evaluated 53 radiocarbon dates from the old copper complex. In their own words, the carbon 14 ages push back the oldest known copper artifact age to at least 7,690 plus or minus 40 BP, which calibrates out to approximately 8,500 calendar years before present. The artifact in question is a conical copper point recovered from Vilas County, Wisconsin. On the current evidence, it is one of the oldest pieces of worked metal anywhere in the world. Let that number sit for a moment. 8,500 years ago. That is somewhere around 6,500 BC. The Egyptian Old Kingdom, the era of the Great Pyramids, would not begin for another 4,000 years. The Sumerian civilization, the first urban culture of Mesopotamia, would not establish its cities for another 2,000 years or so. The Bronze Age of the Near East, the era that would eventually consume copper at an industrial scale, was still 3,000 years in the future. The old copper complex people were already working copper, while Europe was still in the Mesolithic, before the wheel was invented anywhere, before the domestication of the horse, before writing existed in any form anywhere. They were not farmers. This is the part that breaks the standard story. The old copper complex people were hunter-gatherers. They hunted deer, elk, moose, bear, and smaller game. They fished, and the abundance of fish bones in the archaeological record tells us how important fish was to their diet. They gathered wild plants. They harvested wild rice in the wetlands. They moved with the seasons. They did not build cities. They did not establish empires. And yet they had developed a metallurgical tradition that no other hunter-gatherer culture in the world is known to have developed at that scale. The old copper complex is, on current evidence, one of the oldest metalworking traditions anywhere, comparable in age to copperworking in the Near East and the Balkans. What does that mean? It means that the assumption built into the standard story that you need cities to develop sophisticated metallurgy is wrong, or at least it is not the whole truth. What you need is the right raw material, the accumulated knowledge to work it, and a way to distribute the products of your labour across a wide geography. The old copper complex people had all of that. They did not need to settle down to figure it out. They figured it out while moving. The cemeteries excavated in the 1940s, 1950s and 1960s gave archaeologists their first detailed look at who these people were. The most famous of these is the Oconto site in Wisconsin, which was discovered in June of 1952 by a 13-year-old boy named Donald Baldwin, who was digging in an abandoned gravel quarry on the outskirts of his town. He found bones, he told his father. His father told the local authorities. The Milwaukee Public Museum and the Wisconsin Historical Society sent an expedition led by Robert Ritzenthaler, Warren Witchery, and Arthur Niehoff. They began excavating that summer. What they found was a cemetery. Excavations recovered the remains of a number of individuals. Published estimates range from about 45 to 52, with the broader site likely containing more burials that had been lost to the gravel quarrying that had been going on for decades before the find. The bodies were buried in a variety of ways. Some were extended, some were bundled, the bones gathered together and interred as a package. Some had been cremated. The variety suggested a long use of the site by people who returned to bury their dead, generation after generation, century after century. With the bodies were grave goods. 26 copper artefacts were recovered from the Oconto site. 7 awls, 4 crescent-shaped objects of uncertain function, 3 clasps, a socketed tang point, a fishtail point, an ovoid point, a fishhook, a bracelet, a piece of spiral-coiled tubing, a rivet, a spatula, and 4 small fragments. Around the copper, side-notched chert projectile points, shell beads, and, buried with a juvenile, a swanbone whistle. A whistle, made from the wing bone of a swan placed with a child thousands of years ago. Yeah, in a place that the people thought was important enough to use as a burial ground for centuries. In 1953, a carbon sample from the Oconto site was sent to W.F. Libby, the inventor of radiocarbon dating, at the University of Chicago Institute for Nuclear Studies. It was the first radiocarbon date ever obtained from a prehistoric site in Wisconsin. The result came back as 5,600 plus or minus 400 years before present. At the time, this made Oconto the oldest dated site in Wisconsin, and one of the oldest dated burial sites in eastern North America. Later work, including the broader chronological surveys by the Pompiani team, has placed the main Oconto burial activity within a range of approximately 5,000 to 6,000 years ago, consistent with that original 1953 measurement. But the Oconto burials are sophisticated as well as old. The copper objects show evidence of skilled metalworking, annealing, cold hammering, the use of forms to create consistent shapes. The diversity of artifact types indicates that the technology had moved beyond raw experimentation into a settled tradition. The presence of trade items, shells from the Gulf of Mexico, from species that live nowhere near Wisconsin, shows that the people who buried their dead at Oconto were embedded in long-distance exchange networks. The Menominee Indian tribe of Wisconsin claim the burials at Oconto as their ancestors. The burials predate the Native American Graves Protection and Repatriation Act of 1990 by 38 years, which is part of why the material was excavated and removed at all. Today, the management of those remains is handled with the involvement of tribal consultation that was simply absent in 1952. The Oconto site was not unique. Similar cemeteries have been found at Ray in Wisconsin, at Osceola, at Riverside in Michigan, on the Ottawa River in Quebec. The same suite of artifacts shows up at each one, the same range of dates, the same impression of a sophisticated material culture that did not bother to build cities, write books, or domesticate plants, but worked metal with a fluency that the rest of the world would not match for thousands of years. There is one more thing that needs to be said about the old copper complex people, because it is sometimes lost when we focus on the metal. They had what archaeologists call a complex chipped stone industry as well. Fine projectile points made from chert, drills, scrapers, knives. They had groundstone tools, banner stones and atlatl weights among them, along with bone tools and shell ornaments. They were not a one-trick culture. The copper was the most striking part of what they did. It was not the only part. It is worth saying clearly, these were not primitive people who happened to stumble onto a rich deposit. They were sophisticated, mobile, networked. They had figured out a way of life that worked, that supported large enough populations to maintain a continent-spanning trade network, and that allowed them to extract and distribute metal on a scale that nobody else in the Americas was attempting. The reason we keep being surprised by them is that they do not look like what we expect a culture capable of all this to look like. That is not their problem. That is ours. To understand why the Lake Superior copper deposits are the way they are, you have to go back about 1.1 billion years. That is not a typo. 1.1 billion. With a B. At that time, the North American continent was beginning to crack. A great fissure opened, running from what is now Kansas up through the Great Lakes region and out the other side. Geologists call it the Mid-Continent Rift. For about 20 million years, lava poured out of this rift in vast sheets. Hundreds of individual flows stacked on top of each other, eventually forming a pile of basalt more than 15 kilometers thick. Most rifts on Earth eventually finish what they start. They open all the way and become oceans. The Mid-Continent Rift did not. Something stopped it. Exactly what geologists are still debating. The most current models, based on the work of Theodore Bornhorst and others at Michigan Technological University, suggest that a major compression event later in the rift's history may have done something unique. It squeezed the rocks. It created fractures and faults. And through those new pathways, hydrothermal fluids rose. These fluids were hot. They were chemically active. They carried copper in solution. And as they rose through the basalt and the conglomerate layers that had formed between lava flows, they cooled, they reacted with the surrounding rock, and they deposited their copper. But they did not deposit it the way copper is deposited almost everywhere else on Earth. Almost everywhere else, copper comes out of solution as a sulfide or an oxide bound to other elements, formed into ore that requires processing. Chalcopyrite, bornite, malachite, azurite. You have to smelt them. You have to break the chemical bond between copper and whatever it is attached to. That is what the metallurgists of Cyprus and Anatolia and the Iberian Peninsula learned how to do. In the Quin ore, the copper came out as metal, pure, native, already in the form of copper, just sitting in voids and cracks in the rock. This is exceedingly rare on Earth. It happens in a few places, in trace amounts. Nowhere else does it happen at the scale it happened in the Mid-Continent Rift system. The Quin ore Peninsula and Isle Royale together contain the largest known concentration of native copper anywhere in the world. The copper is typically very high purity. Pull it out of the ground, knock the host rock off it, and you have copper. No furnace needed. The native copper occurs in two main forms in the Quin ore. The first is what miners called lacy copper, copper that filled the small bubbles and cavities of cooling lava flows, eventually creating delicate filigree patterns where the bubbles had been. The second is what miners called mass copper or float copper, solid masses of native copper, sometimes weighing thousands of pounds, sometimes more, that had been deposited as the hydrothermal fluids pooled in larger voids. The most famous single mass of native copper recovered from the district in the early historical period was the Ontonagon boulder, weighing 3,708 pounds, roughly 1.85 short tons. Native Americans had known about it and visited it for ceremonial purposes long before any European had heard of it. It was removed in 1843 by the entrepreneur Julius Eldred, eventually confiscated by the War Department, and is today in the possession of the Smithsonian. Other masses, found in the 19th and 20th century commercial operations, were much larger. The largest single mass ever recovered from the district was a 527-ton block at the Minnesota mine, tunnelled into by industrial miners in 1856. The ancient miners had encountered some smaller, but still impressive masses too. The 6-ton mass of pure copper that S.O. Knapp's Minnesota Mining Company found in 1847, in the bottom of an ancient pit 26 feet deep, was just one of many. It had been raised on wooden cribbing. Oak billets supported it. The wood had lost all of its consistency to the point that a knife blade could be thrust into it as easily as into a peat bog. Whoever had been working the pit could not move masses of that size out of it. So they had left them there, sometimes after cutting smaller pieces off the edges. What did all of this look like to the people who lived on the surface? The country, the way it looked about 10 or 12,000 years ago, was very different. The continent had been buried under more than a mile of ice for tens of thousands of years. Then the ice began to melt back. Lake Superior was forming out of the meltwater, larger then than now, with different shorelines. As the ice retreated, it scraped and ground the rock beneath it. In the Quinault, the glacier was doing something unusual. It was gouging right through the basalt and the conglomerate that hold the copper deposits. And as it did, it was plucking pieces of copper out of the rock and carrying them along, sometimes for tens of miles. Then, when the glacier finally melted, it dropped them. The result in the early Holocene period, the time of the first human settlement of the Great Lakes region, was a country where copper was visible on the surface, in veins to be quarried, as boulders, as float copper sitting in stream beds, washed out of moraines, as nuggets you could find by walking along beaches and looking down. Based on what we know about the geology and the available technology of the period, we can reconstruct how this would likely have started. The first copper used by the people who came into this region after the glaciers retreated was probably picked up off the ground, cold hammered, shaped into ornaments and tools. The technique spread, the tradition developed, and as the easy surface copper was used up, the people who knew how to find more of it began to look at the rock itself. They began to dig. The early shafts were probably shallow, trench-like, following the surface expression of a copper vein down into the rock beneath. But over thousands of years, as the technique was refined, the shafts grew. Some, by the time the ancient miners were finished with them, were more than 20 meters deep. And here is a number worth holding. Between 1845, when commercial copper mining began on the Quinault, and 1996, when the last mine closed, the district produced approximately 15.5 billion pounds of refined copper from 380 million tons of ore. That is the number from professional industrial extraction with steam engines and dynamite and rail systems. The deposits that produced it were the same deposits the ancient miners had been working with stone tools and fire for thousands of years before. The Lake Superior copper deposit is, by any measure, one of the great mineral concentrations on Earth. It is the only place on the planet where native copper was the primary product through the entire history of commercial mining, and it was being worked by people with stone tools and fire for thousands of years before the wheel was invented anywhere else. The geology of this place was unique on Earth. The technology that responded to it was a unique answer to that geology. And what the people of the old copper complex built on top of those two things, we still do not fully understand what kind of society it was. There is a temptation, when we think about ancient labour, to imagine it as primitive, slow, inefficient. We picture people scratching at rock with bone tools, making tiny progress over generations, achieving in centuries what a modern machine could do in an hour. Some of that is true for some ancient labour. It is not true for what happened at Lake Superior. The miners of the old copper complex were extraordinarily efficient at the one thing they were trying to do, get copper out of basalt. They had developed a technique that was, for the materials available to them, close to optimal. Whether the technique was invented locally or imported from somewhere else is one of the unanswered questions. What we can say with certainty is that they were using it for at least 6,000 years, and they kept refining it the whole time. The technique was called fire setting. It worked like this. First, you identified the copper-bearing rock. The miners were extremely good at this. The deposits on the Quinault and Isle Royale do not appear randomly. They follow patterns in the geology, particular kinds of basalt flows, particular conglomerate layers, particular zones in the rock where the hydrothermal fluids had pooled. The ancient miners knew these patterns. Their pits track copper veins with a precision that 19th century professional surveyors found astonishing. This implies something specific, a body of geological knowledge accumulated across many generations, taught and refined as it was handed down. They went to the copper. They did not stumble across it. Second, you built a fire on top of the rock you wanted to break. Not a small fire, a large, sustained fire, large enough to heat the surface of the rock to a high temperature. The miners brought wood to the site. They kept the fire burning long enough to deeply heat the rock all the way down, well past the surface. Third, and this is the elegant part, when the rock was hot, you doused it with cold water. Lake Superior is, by the standards of inland water bodies, frigid. Even in midsummer, the surface temperature rarely exceeds the high 50s Fahrenheit. The deeper water is in the 30s and 40s year-round. The water carried up to the pits was shockingly cold. When it hit the heated rock, the thermal differential was extreme. The rock fractured. The fractures opened along natural weaknesses, the same fractures that the original hydrothermal fluids had used to deposit the copper in the first place. The copper embedded in the now cracked rock was suddenly easier to extract. The miners moved in with stone hammers and broke off pieces of the surrounding rock until the metal was exposed. The hammers themselves are the most common archaeological artifact at the sites. Thousands of them have been recovered. They are made of basalt or granite, cobbles selected from the beaches and stream beds of the region. They are sized for human hands. Many are grooved around the middle, where a wooden handle would have been attached with rawhide. The grooved ones were probably hafted as proper hammers. The ungrooved ones were probably held in the hand directly. The sizes vary enormously. The National Park Service interpretive materials note hammers of up to 40 pounds at typical sites. Henry Gilman, the 19th century archaeologist whose work I've been quoting, described stones in a single pile that range from about 1 pound to between 60 and 75 pounds. The smaller ones were probably for fine work. The larger ones, and these are the ones that demand a moment of reflection, were used for heavy demolition. 40 pounds of basalt or more swung with both arms against a rock face, over and over, for days. Some of the hammerstones show evidence of repeated use. Their edges are battered, their corners are rounded. They have been used until they could no longer be used. Other tools at the sites included wooden bowls for bailing water out of the pits as they filled with rain and groundwater, wooden levers for prying loose blocks of rock away from the working face, wooden wedges, sometimes split into thin strips that could be driven into a crack, then wetted so the wood swelled and the crack widened. All of these have been recovered, in varying states of preservation, from the waterlogged conditions at the bottom of some of the deeper pits. The fact that wooden artefacts survived at all is itself a small miracle. Wood does not normally last for thousands of years, but in the constantly cold, constantly damp environment at the bottom of a copper pit on Isle Royale, the conditions were just right for organic preservation. Some of the wooden artefacts recovered in the 1850s and 1860s, and the embedded organic material recovered more recently, have been radiocarbon dated across a range of ages, contributing to the chronology the Pompiani team has been building. The work itself was almost certainly seasonal. Isle Royale, in particular, is an island. It is reached today only by ferry or seaplane. The closest mainland approach is about 14 miles north to Minnesota, and the longer crossings from the Keweenaw side run upwards of 50 miles across cold, often violent open water. In the late Archaic period, the crossing would have been made in dugout canoes or birch-bark boats. Based on what we know about the regional climate of the time, the crossing would have been impossible in winter. The ice on Lake Superior, when it forms, is not the kind of ice you can walk on for those distances. The pattern almost certainly was this. The ancient miners came to the island in the spring or summer. They worked. They left before the storms of late autumn made the crossing too dangerous. This seasonal pattern shows up in the archaeology. The sites near the mines do not contain the kind of permanent settlement debris you would expect from year-round habitation. There are no winter houses, no extensive storage pits, no deep midden accumulations of the sort that mark long-occupied villages. What you find instead is the residue of camps, short-term, work-focused, with the food remains of fish and small game, the broken hammerstones, the discarded charcoal of the fires, and very little else. The miners came, did their work, and went home. They left almost no permanent mark on the surface, except for the pits themselves and the piles of stone tools and the heaps of poor rock that they had not bothered to carry away. This brings us to a question that the older generation of archaeologists tended not to ask, but that the more recent generation cannot avoid asking. Where was home? If the mines were a seasonal destination, then the people who came to them were coming from somewhere. Based on what we know about the regional archaeology, we can infer that the communities working the copper deposits maintained permanent base camps elsewhere, likely in the river valleys to the south, in the lakeshore areas of central Wisconsin and Michigan, in the upper Mississippi watershed. Those communities have been harder to find than the mining sites, partly because their archaeological signatures are mixed with the signatures of other archaic period peoples who were not specifically connected to the copper trade. The evidence pieces together into a clear inference. They were there. They had to be there. The mines themselves were a workplace. The communities that supplied the workforce were elsewhere, and the copper that came out of the workplace was distributed elsewhere again, across a trade network that we will get to in the next part. This is, in some ways, the strangest thing about the old copper complex. It looks structurally like an industrial extraction operation. You have specialized work sites, organized labor, established techniques, and distribution networks. You have what amounts to a multi-generational mining tradition. What you do not have is any of the typical infrastructure that we associate with industries of this kind. No cities, no bureaucratic centers, no written records, no clear political hierarchy. The work was done. The product was distributed. The system functioned for thousands of years, and it functioned without any of the apparatus that we, looking back, would consider necessary for it to function. This is the part that gets us closer to the unsettling truth at the heart of the old copper complex. The standard story of how complex things get done assumes you need a king, or a council, or a class of administrators. The old copper complex got it done without any of that, or at least without any of that being visible to us at this distance. The miners knew what they were doing. Somebody coordinated it. The system worked. We just cannot see anymore who was holding it together. Let's talk about numbers, because the numbers are where this story stops being a curiosity and starts being a problem. There are several different ways to estimate how much copper was extracted from the Lake Superior region during the ancient mining period. Each method gives a different answer. None of them gives a number that has been definitively reconciled with the artifact record. Method 1. Count the pits. The most rigorous surveys identify more than 5,000 individual mining pits and excavations distributed across the Quinault Peninsula, the Porcupine Mountains region, and the islands of western Lake Superior. On Isle Royale alone, an island measuring roughly 45 miles long by 9 miles wide, early surveys identified more than 1,000 pits, with the Minong Mining District alone designated a National Historic Landmark in 2021, containing in excess of 0 pits in one concentration. Multiply the number of pits by the average estimated volume of each pit. Account for the copper, recovered as a percentage of the rock removed. Convert into tons. The result, depending on which set of assumptions you use, lands somewhere between tens of thousands of tons at the conservative end and several 100,000 tons at the upper end of mainstream estimates. Some alternative history sources cite figures of 500,000 to 800,000 tons. That higher figure is widely quoted in popular literature about the topic, but it is not anchored in any peer-reviewed geological survey, and the methodology behind it is unclear. The honest range, based on what the academic literature actually supports, is tens of thousands to hundreds of thousands of tons, possibly more. The total extracted has never been definitively established by a comprehensive modern survey. Method 2. Use the lead pollution signature. This is the approach pioneered by David Pompiani and his colleagues, whose work I have mentioned several times. They reasoned that the fire setting technique, and especially the annealing of copper in wood fires afterward, would have volatilized trace amounts of lead from the copper, from the surrounding rock, and from the wood smoke itself. That lead would have settled into nearby lakes, accumulating year by year in the sediments. By drilling sediment cores from lakes near the ancient mining sites and measuring lead concentrations layer by layer, they could build a record of mining intensity over time. The results, published in 2013 in Environmental Science and Technology, were striking. The Quinault Peninsula lakes showed clear lead pollution signatures starting around 8,000 years ago. The pollution intensified. It peaked around 6,000 years ago. It continued at substantial levels for thousands of years. The team's subsequent work, including a 2015 study on Macargo Cove on Isle Royale, confirmed that the pattern extended to the islands. Mining-related pollution at Macargo Cove was detected between approximately 6,500 and 5,400 years ago. A 2022 follow-up study led by Catherine Vall found atmospheric lead deposition at additional Isle Royale lakes, Lily Lake and Pond 2, that confirmed mining-related pollution had been carried by air across the island. What the lead record cannot tell us directly is how much copper was extracted. What it can tell us is that the extraction was sustained, regional and intense, at a level the team interpreted as comparable to small-scale industrial operations in other parts of the world thousands of years later. The pollution signature is what you would expect from heavy-handed mining over millennia. It is not what you would expect from occasional opportunistic small-scale activity. Method 3. Count the artifacts. This is where the gap becomes visible. Across the entire archaeological record of North America, in every burial site, every cache, every accidental find, every museum collection, the total inventory of copper artifacts associated with the old copper complex tradition and its successor cultures, the Hopewell, the Mississippian, and others, amounts to a relatively modest figure when compared to the higher estimates of total extraction. Even granting the most conservative academic estimates of total extraction, the artifact total falls considerably short of accounting for it. The standard explanation is that most of the artifacts simply have not been found yet. They are buried in unexcavated sites, corroded into the soil in places we have not looked, sitting in private collections and basement boxes and unreported finds. This is, in principle, plausible. Native copper does not disappear. Once extracted, it persists. Copper that goes into the ground stays in the ground. But the gap has been present in the academic discussion since the 19th century. The expectation, when the mining was first documented in the 1840s and 1850s, was that as American archaeology developed, the artifact total would gradually rise to meet the extraction total. It has not fully. The gap has narrowed. It has not closed. The mainstream position is that ongoing fieldwork and improved survey methods will, in time, close it further. Some researchers find this fully adequate. Others, and this is where the argument gets interesting, do not. This is the central scale problem, and it is, despite a long tradition of academic discomfort with it, a real and ongoing question. The standard model treats this as a we haven't looked enough problem. The Pompiani team's lake sediment work has, if anything, complicated the picture rather than simplifying it, because it has confirmed how intense and sustained the mining activity actually was. A useful comparison. Cyprus is the most famous copper-producing region of the ancient Mediterranean. Cypriot copper production in the Bronze Age has been studied for more than a century. Geologists and archaeologists have a relatively clear picture of how much was extracted, where it went, and what fraction of it is reflected in the artifact record of the Eastern Mediterranean. The math for Cyprus more or less works. The Mediterranean's artifact total is broadly consistent with the known output of Cyprus, augmented by smaller production from Sardinia, the Laurion in Greece, Anatolia, and the Araba. For the Lake Superior region, the equivalent calculation is harder to close. There is more uncertainty, more open ledger. What is open is the territory we're going to spend the rest of this video inside. The first place to look for the missing copper is within North America itself, because the people of the old copper complex were not isolated. They were not, despite what older histories sometimes suggested, living in small communities cut off from the rest of the continent. They were, on the contrary, embedded in one of the largest exchange networks the ancient Americas ever produced. The evidence is everywhere you look. In the burials at Oconto, alongside the copper, archaeologists found shell beads. They were not local shells. They came from the Atlantic and Gulf coasts, sometimes from a species called lightning whelk, which lives in shallow tropical waters more than 1,000 miles from Wisconsin. To get from the Gulf of Mexico to a burial site in northeastern Wisconsin, those shells had to pass through many hands, across many languages, over many years. The copper went the other way. Copper artifacts that show all the hallmarks of Lake Superior origin, the purity, the working technique, the typology, have been found across an enormous area. They have been recovered in Tennessee, in Kentucky, in southern Illinois, in the Ohio River Valley, across the Great Plains as far west as the eastern Dakotas, Saskatchewan, and even Alberta, north into Manitoba and Ontario, east along the Ottawa River into Quebec, and as far as parts of New England. In some places, the copper appears in larger concentrations, in other places only as isolated finds. The total distribution covers most of eastern North America and a substantial portion of the Central Plains. This was not opportunistic exchange, this was systematic. The trade ran along established routes, river systems, lakeshore portages, overland paths that had been in use for generations before the old copper complex emerged and would continue in use for generations after it declined. The Mississippi, the Ohio, the Illinois, the Missouri, the Great Lakes themselves, used as a kind of inland sea for the movement of goods. The trade in copper was part of a larger trade in obsidian from the western volcanic regions, marine shells from the coasts, exotic stone from the upland sources, animal products of various kinds. The old copper complex sat at one node of this network. The mines at Lake Superior were the source of the copper. The communities along the rivers and lakes were the intermediaries. The destinations were everywhere from the Atlantic coast to the western plains. There are some specific finds worth mentioning, because they illustrate how far the copper travelled. A copper working tradition in the Mississippi Valley centuries later would build directly on this earlier network. The Hopewell culture, which flourished from approximately 100 BC to 500 AD across the Ohio and Mississippi valleys, used copper extensively in their ceremonial objects, ear spools, breastplates, headdresses. The source of the Hopewell copper has been studied. Most of it appears to have come from the same Lake Superior region that the old copper complex people had been mining thousands of years earlier. The Mississippian culture, which came later still, did the same. They produced the famous copper plates of the southeastern ceremonial complex, ritual objects depicting birdmen, warriors, mythical beings, and again, much of the copper was Lake Superior in origin. In other words, the trade network the old copper complex established did not die with them. It became the foundation for everything that came after. The Hopewell and the Mississippian peoples used the routes the earlier copper traders had established. They extracted more copper from the Lake Superior region, though probably at lower volumes than the Archaic period peak, and they continued the long-distance distribution. Now here is the important point about all of this for our central question. The continent-wide trade network is real. It is well documented, and on the higher estimates of total extraction, it still does not fully account for the gap. If you take all of the copper that has been recovered from all of the sites across the continent, Old Copper Complex period, Hopewell period, Mississippian period, all of it added together, and you compare that total against the upper range estimates of how much was extracted during the peak Old Copper Complex period alone, you come up short. The trade network distributed an enormous amount of copper across an enormous area, and on those higher estimates, it still does not fully balance with what the mines produced. Some researchers have argued that the standard estimates of total extraction are too high, and that if you lower them sufficiently, the math works out. This is possible, but the lake sediment evidence, the lead pollution signature, does not strongly support a major downward revision. The pollution levels are consistent with sustained large-scale activity. They are not consistent with a small operation that has been wildly overestimated. Other researchers have argued that the artifact total is significantly undercounted, and that future archaeological work in unexcavated parts of the eastern United States and Canada will eventually close the gap. This is the most common mainstream position. The American interior has not been excavated as thoroughly as, say, the Mediterranean basin. There may be very large quantities of copper artifacts still in the ground. That mainstream position is reasonable. It is also slow. It has been the working hypothesis for 150 years, and while the gap has narrowed, no decisive closure has come. The deeper question, which the trade network analysis cannot answer, is whether all of the copper was distributed within North America at all. This is where the discussion has to expand beyond the continent. If the artifact record of North America, even fully accounted for, cannot accommodate the highest estimates of total extraction, and if the lake sediments confirm that the extraction was as large as those estimates suggest, then either the artifacts are still mostly hidden, or some of the copper went somewhere else, or the extraction estimates need to come down. The trade network, as we understand it, is a North American story. It is a story of rivers and portages, of Wisconsin and Ohio and the Mississippi Delta. It does not extend across oceans, it does not cross the Atlantic, but there is a copper supply problem on the other side of the Atlantic, at roughly the same time, that has been sitting in the academic literature for decades. And that problem brings us, whether we want to go there or not, to the question that the mainstream archaeological community has spent a long time trying to put to rest. I want to be very careful with this part. The questions we're about to look at are real questions. The evidence on both sides is real evidence, and the conclusions in either direction are not settled. What I am about to lay out is the actual state of the academic discussion on a controversy that has run for more than a century. I'm not going to tell you what to believe. I'm going to tell you what the evidence shows, what it does not show, and where the honest researcher should stop. The Bronze Age, in the conventional Old World chronology, ran roughly from 3300 BC to 1200 BC. Its defining feature was the alloy that gave it its name. Bronze is a mixture of copper and tin, and sometimes other elements, like arsenic in the earlier phases. Bronze is harder than copper. It holds an edge better. It is more useful for weapons, tools, and ornaments. The discovery of how to make bronze and the establishment of trade networks to supply both copper and tin to the manufacturing centres was one of the great technological revolutions of human history. The civilizations that ran on bronze were enormous by ancient standards. The Egyptian New Kingdom, the Hittite Empire, Mycenaean Greece, Minoan Crete, the various city-states of the Levant, Ugarit, Byblos, Tyre, Sidon, the Assyrians, the Babylonians, the Indus Valley civilizations to the east. All of them consumed copper at industrial scale. They made weapons by the tens of thousands. They cast statues, fittings, vessels, ornaments. They armed their soldiers. They equipped their navies. They traded with each other in a network of palace economies that has been called the first global system. Where did all of that copper come from? The traditional answer is Cyprus. The very name of the island, Kypros, in Greek, became the root of the word copper. Cyprus had rich deposits of copper in the Troodos Mountains, and from the early Bronze Age onward it was a major producer. Sites like Hala Sultan Tekke and Enkomi grew up around the copper trade. The Uluburun shipwreck, found off the coast of southern Turkey and dated to the late 14th century BC, carried about 10 tons of copper in ox-hide-shaped ingots. Isotopic analysis has shown that nearly all of that copper came from Cyprus. But Cyprus was not the only source. Sardinia produced copper. Anatolia had its own deposits, including the Ergani mines of southeastern Turkey. The Laurion region of Greece near Athens was a significant source as well, and recent isotopic studies suggest that for late Bronze Age Crete, the Laurion may have been even more important than Cyprus, contributing a substantial fraction of the copper used in some periods. The Arabah, between Israel and Jordan, was a smaller but documented source. Iberia, the Spanish and Portuguese peninsula, had copper deposits that were worked at various points. North African sources existed, so there were sources. There was a known set of producers, a known set of trade routes, a known set of refining centres. The Mediterranean Bronze Age did not have a single source for its copper, it had a network. Here is where the problem starts. The total quantity of copper that the Bronze Age civilizations of the Eastern Mediterranean consumed over roughly 2,000 years has been estimated by various researchers. The estimates vary, but they are all very large. When you add them up and you compare them to the known production capacity of the documented sources, you sometimes get an awkward result. The math does not always quite work. The documented sources, even at maximum sustained output, may not be sufficient to account for all of the copper that was used at the peak of the Bronze Age. This is not a fringe observation. It is discussed openly in the academic literature on Bronze Age metallurgy. There are several possible explanations. Maybe the consumption estimates are too high. Maybe the production estimates from the known sources are too low. Maybe there were significant sources that have not yet been identified, undiscovered Anatolian mines, smaller Mediterranean operations, deposits in the Black Sea region or the Caucasus. Maybe the recycling of copper was much more extensive than has been assumed. Each of these is plausible. None has been definitively confirmed. And then there is the more controversial possibility, the one that mainstream archaeology, with very few exceptions, has spent a long time pushing back against. The possibility that some of the copper came from somewhere outside the Old World altogether. The Lake Superior native copper has one property that makes it interesting to this discussion. It is, as I mentioned earlier, extraordinarily pure. Bronze made with high purity copper has certain chemical and physical signatures that are different from bronze made with lower purity copper. When researchers have analysed Bronze Age artefacts in European museum collections, they have found that some of them, not all of them, not even most of them, but some are made of copper of very high purity comparable to native copper. This is taken, by some researchers, as a hint that the source of some of the copper in those artefacts might have been a native copper deposit rather than a smelted ore deposit. The Mediterranean did not have significant native copper deposits. The Lake Superior region did. A handful of isotopic studies have been published over the years that claim to find North American geological signatures in specific Bronze Age artefacts. The claim is that the isotopic ratios of lead trace impurities, the same ratios that have been used to source copper to Cyprus, Lorient, and other Mediterranean sites, match Lake Superior copper better than they match any known Old World source. The mainstream response to these studies has been highly sceptical. The methodology has been challenged on technical grounds. Some of the studies have been criticised for inadequate sample sizes. Some have been criticised for selecting artefacts in a way that biases the results. Some have been criticised for not adequately accounting for the recycling of copper, which can mix isotopic signatures and complicate sourcing. The legitimate scientific response to these methodological problems is to do better studies, larger samples, cleaner methodology, replication by independent labs, a comprehensive isotopic survey of Bronze Age copper artefacts in European collections, compared against a well-characterized signature for Lake Superior native copper, could in principle resolve the question. That comprehensive survey has not been done. Other lines of evidence cited for transatlantic copper trade in the Bronze Age are softer. They include similarities in mining techniques between Lake Superior and Mediterranean operations, though this could easily reflect convergent development, since fire setting was the standard technique for hard rock mining everywhere before the invention of explosive. Certain typological similarities between mining tools have also been cited, though these are also subject to convergent development explanations. And there is the haplogroup X genetic marker, which we will discuss in a later part. The most serious objection to the transatlantic hypothesis is the lack of any direct evidence of contact. No securely dated Bronze Age artifact has been recovered from a North American archaeological context. No North American artifact has been recovered from a securely dated Bronze Age context in the Old World. No shipwreck has been recovered that would document a transoceanic voyage. No inscription, no chart, no account in any ancient document has been found that describes a North American source of copper. So where does this leave us? It leaves us with a genuine, unresolved puzzle. The Mediterranean Bronze Age had, at peak demand, a tight copper supply. The Lake Superior region had a missing copper question. The dates of major activity in both regions overlap. The properties of the copper are interestingly compatible. The isotopic evidence is suggestive, contested, and incomplete. The direct evidence of contact is absent. The honest position is that the transatlantic hypothesis is not proven. It is also not definitively disproven. It is in a kind of academic limbo where most professional archaeologists treat it as unlikely, where a minority of researchers treat it as worth investigating, and where the technical work that could actually settle it has not been done. What I want you to take away from this section is not a verdict. It is a sense of where the actual edge of knowledge is. The Bronze Age copper supply question is real. The Lake Superior missing copper question is real. Whether they are connected is open. Anyone who tells you it is definitely yes is overstating the evidence. Anyone who tells you it is definitely no is doing the same thing. The history of science is full of examples of questions that sat in this kind of a limbo for decades before some new technique or some unexpected discovery finally resolved them. This may be one of those questions, or it may not. We do not know yet. What we know is that the question is real, and it has been sitting unanswered for a very long time. At some point, the heaviest mining activity ended. This is one of the few things about the Lake Superior Copper District that most researchers agree on. The mainstream archaeologists agree. The Pompiani team's lake sediment data agrees. The artifact record agrees. The patterns of trade agree. Whatever else is uncertain about the old copper complex, the change in intensity is visible in the record. It is the timing of the change, and what caused it, that has not been adequately explained. The lead pollution signature in the lakes near the mining sites is the cleanest indicator. The signature shows a sustained pattern of intense mining activity from approximately 8,000 years ago to approximately 5,400 years ago. After 5,400 years ago, that is, after about 3,400 BC, the signature drops. Not gradually, drops. The 2015 Pompiani paper on Macago Cove explicitly noted what the authors called a coherent cessation of lead emissions at multiple sites in the region, beginning around that date. Other measures show a similar pattern with some variation. The radiocarbon dates on copper artifacts in the trade network show that production continued at lower levels for thousands of years after the lead pollution drops. Copper continued to be worked, and copper continued to be traded throughout the late Archaic period and into the woodland period. But the very heavy industrial-scale extraction that the lake sediments record, the activity that was leaving its strongest fingerprint on the regional atmosphere, that ended. By about 3,000 years ago, copper had largely shifted from a utilitarian material to a prestige material. The old copper complex period had been characterized by heavy production of useful tools, spear points, knives, awls, axes, fish hooks, functional objects. But starting around 1000 BC and accelerating through the woodland and Mississippian periods, copper increasingly appeared in burial sites as ornaments, ceremonial objects, status markers, ear spools, beads, plates with religious imagery, headdresses for high-status individuals. The standard explanation for the shift is that as the broader cultural and economic systems of eastern North America became more complex, as agriculture spread, as larger settlements developed, as religious institutions formed, copper took on social meanings that it had not previously had. It became a marker of status. It was reserved for the elite. The everyday utility of copper tools was replaced by the symbolic value of copper ornaments. This is a reasonable explanation. It probably accounts for a significant part of the shift. But it does not, on its own, fully explain the abrupt drop in the lake sediment record around 3400 BC. The shift to ceremonial use happened later, not earlier. Something else seems to have caused the initial pullback. One factor that the Pompiani team identified, in their 2015 paper, is climate. They noted that the cessation of the lead emissions around 5,400 years ago coincided with the onset of significantly drier conditions in the regional paleoclimate record. The Great Lakes region was getting hotter and drier, lake levels were dropping, forest composition was shifting, the whole regional ecology was under stress. This might have made it harder to sustain the labour-intensive mining operations. The miners might have been pulled away by changes elsewhere in their subsistence base. This explanation is plausible but partial. The mining did not entirely stop in 3400 BC. It continued at lower levels for thousands of years. Why did the climate stress reduce the activity but not eliminate it? Why did the activity resume at higher levels in some periods and then drop again? There is another candidate for what contributed to the longer-term decline. It is more speculative. It involves the Bronze Age collapse of around 1200 BC, which postdates the Pompiani team's coherent cessation by roughly 2,000 years, and therefore cannot be the direct cause of the initial 5,400 years ago drop. But the Bronze Age collapse may be relevant to the further decline of copper production through the late 2nd millennium BC, and to the question of why the heaviest extraction never recovered to its earlier intensity, if there was any connection between the two regions. The Bronze Age collapse, as we mentioned earlier, was one of the most catastrophic episodes in ancient history. Between roughly 1225 and 1150 BC, the entire interconnected Bronze Age trading system of the eastern Mediterranean fell apart. The Hittite Empire collapsed, Mycenaean Greece fell, Ugarit, the great trading city of the Syrian coast, was destroyed by raiders, Egypt was severely weakened, trade networks that had run for centuries broke down, cities were abandoned, writing systems went out of use. The Dark Age that followed in some regions lasted for centuries. The causes of the Bronze Age collapse are still debated. The leading hypotheses involve some combination of climate change, a severe, prolonged drought across the eastern Mediterranean, internal palace revolts, earthquakes, the migration of unknown peoples called the Sea Peoples, and systemic fragility in the interconnected palace economies. Most modern researchers see the collapse as a perfect storm of multiple simultaneous stresses that pushed already fragile societies past their tipping point. If, and this is a significant if, the Lake Superior copper had been part of the Bronze Age trading network at some scale, then the collapse of that network would have removed a major source of demand. The miners on the other side of the Atlantic would have lost their export market. The activity that had been driven by that demand would have slowed, and in fact the archaeological record does show further decline in old copper complex-style production through the late 2nd millennium BC. This is, again speculative. The transatlantic trade hypothesis is not proven. It cannot be used as a confident explanation. But the timing coincidence between the Bronze Age collapse and the apparent further reduction in Lake Superior copper activity has been noted by several researchers and remains one of the harder things to explain away on either side of the question. There is one more possibility worth mentioning. The miners may have been displaced. The people who had been doing the mining for thousands of years may have been driven out, replaced, or absorbed by other populations. The late Archaic period in North America was a time of significant population movement and cultural change. The old copper complex was a specific cultural phenomenon associated with specific groups. Those groups did not necessarily continue to exist as distinct entities indefinitely. As they merged with or were displaced by other groups, their characteristic technological practices may have transformed. But here, again, is the strange thing. The copper did not run out. The deposits that the ancients had been working contained, and still contain, vast quantities of copper, much of which was only later removed by 19th and 20th century industrial mining. There is, by some estimates, still more copper in that rock than has ever been mined out of it. Whatever made the ancient miners step back, it was not the exhaustion of the resource. The resource is still there. So we are left with a question that has not been definitively answered. The largest known ancient mining operation in the early Americas reduced its intensity dramatically, not from running out of material, not from a single identifiable cause, from some combination of climate stress, network disruption, population change, and other factors that we cannot, at this distance, fully untangle. The miners walked back. They left some of their tools beside the pits, along with the larger copper masses they had not been able to carry out. Fish bones lay on the floors of the deep shafts, and the heaviest extraction did not resume. Now we come to one of the more contested pieces of evidence in this whole discussion, and I want to handle it carefully, because there is a great deal of misinformation about it on the internet. Mitochondrial haplogroup X is a real genetic marker. It is one of several haplogroups, branches of the maternal genetic lineage, that geneticists use to trace ancient population movements. It is found, in varying frequencies, in several places around the world. In the Americas, haplogroup X, specifically a subclade called X2A, is most prominent in the indigenous peoples of the Great Lakes region. The Ojibwe, also written as Chippewa, the Algonquin, related Algonquian-speaking groups, and at lower frequencies in some other Native American populations, including the Navajo, the Sioux, and the Nusha-Nulth on the Pacific coast. In Eurasia, the broader X haplogroup is found in parts of the Mediterranean basin, in the Caucasus, in some Anatolian populations, and in scattered groups elsewhere. The geographic pattern is unusual. Most Native American haplogroups, A, B, C, D, have clear distributions across Asia that trace back to the migrations across the Bering Land Bridge during the late Pleistocene. They are found in Siberia and East Asia, where the ancestors of Native Americans came from. Haplogroup X is different. It is rare in East Asia, though related lineages have been detected at low frequencies in Central and Northern Asia, including among Altai populations. This has led to a debate about how haplogroup X reached the Americas. There are broadly three positions in the academic literature. The first position, which is the current mainstream view, is that haplogroup X arrived in the Americas via the same general route as the other indigenous American haplogroups, through northeastern Asia, across the Bering Land Bridge, and into the Americas. The fact that it is rare in modern East Asia is interpreted as the result of later population replacement. The original Pleistocene-era populations that carried X may have been displaced or absorbed by later expansions, leaving X to survive primarily in the Americas. The detection of X-related lineages at low frequency in Altai and other northern Asian populations is consistent with this model. The X2A subclade, in particular, appears to have arisen during the Beringian incubation period itself, which is why it is found only in indigenous Americans and not in any Old World population. The second position, advocated today by only a small number of researchers, is that haplogroup X arrived in the Americas via the North Atlantic, possibly during the Solutrean period, around 17,000 to 21,000 years ago, when the ice sheets covered the North Atlantic and could in theory have been crossed by people moving along the ice edge in skin boats. This is the Solutrean hypothesis. it has been largely rejected by the mainstream archaeological and genetics communities. The most recent analyses of ancient DNA from the Americas, including the Anzic child, Kennewick man, and others, have consistently failed to find evidence of a separate European migration. The geneticists Jennifer Raff and Deborah Bolnick published a particularly thorough critical re-evaluation of this hypothesis in 2015. The Solutrean hypothesis still has a few defenders, but it should not be presented as a serious contender alongside the mainstream view. I include it here only because it appears in the popular literature on this topic, and you may encounter it elsewhere. The third position, which is rarely articulated in mainstream academic publications, but is common in alternative history literature, is that haplogroup X reached North America via some form of Bronze Age transatlantic contact associated with the copper trade. The argument is that the timing of haplogroup X expansion in the Lake Superior region might coincide with the period of intensive copper mining, suggesting movement of people along the same routes that the copper travelled. The honest assessment of the haplogroup X evidence is this: the genetic data is real, the distribution is unusual, the interpretation is contested but heavily weighted toward the Beringian model. The mainstream interpretation is well supported by the available genetic timing studies, which suggest that the X2A lineages in the Americas separated from Old World X lineages tens of thousands of years before the Bronze Age. If those timing studies are correct, and the consensus of the field is that they are, then haplogroup X cannot be evidence of Bronze Age transatlantic contact, because the lineages would have been in the Americas for tens of thousands of years before the Bronze Age began. The presence of X2A in pre-contact remains like Kennewick man also supports this position. The alternative interpretations rest on either questioning those timing studies or proposing that haplogroup X might have arrived in the Americas in multiple waves, with one of those waves potentially associated with later contact. Neither of these has gained traction in mainstream genetics. For the purposes of our central question about the Lake Superior copper, the haplogroup X evidence is interesting but not strong support for the transatlantic hypothesis. The mainstream interpretation has good evidence behind it, and the Bronze Age contact hypothesis has very little genetic support specifically. What the haplogroup X question does is point at the genuine complexity of ancient population history in the Great Lakes region. The history is more complicated than the simplest version of the migration story would predict, but that complexity is most likely the result of deep time movements during and after the Beringian incubation period, not later transatlantic contact. Honest researchers acknowledge what the evidence supports and what it does not. Anyone who tells you definitively that haplogroup X proves contact with the Mediterranean is overstating the evidence well beyond what it can support. The mainstream verdict on this particular line of evidence is fairly clear, and it does not point where the alternative theorists want it to point. Treat it that way. One of the most persistent claims in popular treatments of the Lake Superior copper mystery is the assertion that the ancient mines were emptied without leaving a trace, that no tools, no bones, no fire pits, no organic remains were found in or around the workings. This claim is not accurate, and I want to spend some time on the actual record. What is actually there is more interesting than the fiction. What the archaeological record actually contains, across the documented mining sites of the Keweenaw Peninsula and Isle Royale. Thousands of hammerstones. These are the most common artifact at the sites by a very large margin. The Milwaukee Public Museum holds extensive collections. The National Park Service has documented them. Photographs from as early as the 1860s show them stacked in piles beside the pit entrances, exactly where they were left when the work stopped. They are not concealed, and they are not absent. They are everywhere, wooden artifacts in significant numbers. The oak cribbing that supported the 6-ton mass at the Minnesota mine near Ontonagon. The wedges used to split rock. The bowls used to bail water. The levers used to raise heavy pieces of copper. These have been recovered from waterlogged context at the bottoms of pits, where the wet, cold, oxygen-poor environment preserved them. Radiocarbon dating of some of these wooden artifacts has yielded dates ranging from a few thousand to several thousand years old, depending on the specific piece. Charcoal from ancient fires. The fire-setting technique left behind ash and charcoal deposits. These have been identified at multiple sites. The charcoal has been radiocarbon dated, providing some of the earliest secure chronological evidence for the ancient mining activity. Animal remains, including fish scales and bones. The meals eaten by the miners during work breaks have been recovered from inside the pits themselves. The Macago Cove find described in part 1 of this video with its scattering of fish scales mixed in with copper chips at the bottom of a 16-foot shaft, is one example. There are others. Bone fragments, sometimes butchered, have been found in association with various working sites across the region. Stone projectile points and other lithic tools. The miners did not only bring hammerstones, they brought their full tool kit. Projectile points have been found in association with mining contexts, indicating that hunting was part of the seasonal activity at the sites. Scrapers, knives, and other lithic implements appear in the assemblages. Copper fragments. Around almost every mining pit, archaeologists find small fragments of copper that were chipped off during the extraction process. The miners did not, contrary to what some popular accounts suggest, somehow remove every trace of the metal from the working sites. They took the larger, useful pieces and left the smaller fragments behind. Those fragments are still being found. A leather bag, 11 inches long and 7 inches wide, was found in October 1863 in an ancient pit at the Hilton Mine in the Ontonagon district. It was lying on a mass of native copper that the ancient miners had unsuccessfully attempted to remove from its parent vein. The bag was sewn with leather string, and from its appearance had been used for transporting mineral. This is the kind of detail that gets lost when people talk about no traces. The traces are specific, and they are sometimes startlingly intimate. What is not prominently represented at the mining sites, and this is genuinely interesting, is the residential infrastructure you would expect from year-round occupation. There are no major village sites adjacent to the mines, no cemeteries at the mining locations themselves, no large food storage facilities of the sort that mark a permanent settlement. This absence is consistent with the seasonal extraction pattern that other lines of evidence also suggest. The miners came, they worked, they left. They were not living year-round at the work sites. The villages where they spent the rest of the year were elsewhere, probably along the rivers and lakeshore environments to the south, where the climate was milder and the resources for daily life were more abundant. This pattern of seasonal extraction by people whose home base was elsewhere is consistent with what we know about how late Archaic period communities operated in the region generally. It is consistent with the mobility patterns documented in other contemporary hunter-gatherer societies. It is consistent, in fact, with what we would expect. But it does raise a question that the older, more dramatic version of the story, the version that claimed no archaeological traces at all, was sidestepping. If the miners were operating from base camps elsewhere, and they were transporting large quantities of copper from the mines to those base camps, and from there into the wider trade network, then we should be able to find traces of that transport. Storage caches, way stations, the residues of where the copper was being processed before it entered the trade routes. We should be able to find all of that. Some of this evidence exists. There are sites along the rivers and lake shores of Wisconsin and Michigan, where significant quantities of unworked or partially worked copper have been recovered, suggesting they served as processing locations. There are caches, relatively small ones, but they exist, of copper that appears to have been being held for later distribution. But the volume of this intermediate stage material is, again, modest compared to the higher estimates of total production. The processing infrastructure that would have been needed to handle those highest estimates is not visible in the archaeological record in the proportions we would expect. So the record is not silent. It is real. It is substantial. It is interesting. It also has gaps. The gaps are not the dramatic total absence that the most sensational accounts describe. They are subtler than that. They are about proportions, about what is there in larger quantities than expected, and what is there in smaller quantities than expected. This is the kind of mystery that real archaeology produces, not movie-set silences, not stripped-bare emptiness, real, complicated, partial, sometimes contradictory evidence that does not quite add up but does not disappear either. It is messier than the popular version. It is also more compelling. There is a strange tendency in popular accounts of the Lake Superior Copper District to talk about the ancient miners as if they belong only to the past, as if they are a vanished people whose descendants are nowhere to be found, as if the question of who they were can only be answered through archaeology, isotope analysis, and the inferences of outside researchers. This is not accurate. The descendants are still here. The Anishinaabe peoples, including the Ojibwe, also written as Chippewa, the Odawa, and the Potawatomi, have lived in the Great Lakes region continuously for at least the last several centuries, and according to their own oral traditions and a growing body of archaeological evidence, much longer than that. The Menominee tribe of Wisconsin claims the burials at the Oconto site as their ancestors. Their oral history places them in the western Great Lakes region for thousands of years. Other indigenous groups, including the various Iroquoian-speaking peoples to the east, also have deep histories in the broader region. These peoples have their own knowledge about copper. Ojibwe oral tradition contains numerous references to copper. The word for the metal in Ojibwe is misquabic, and it appears in stories, ceremonies, and place names throughout the Great Lakes region. The name Minong, the Ojibwe word for Ile Royale, which is now embedded in the official name of the Minong Mining District National Historic Landmark, reflects the long-standing indigenous knowledge of the island as a source of the metal. The Anishinaabe migration story, recorded in numerous forms by indigenous historians and ethnographers, perhaps most accessibly in Edward Benton Benai's The Mishomis Book, first published in 1979, describes a movement of people from the eastern seaboard westward into the Great Lakes region, following prophecies and seeking a specific destination. The story is told differently by different communities, but the general arc includes the establishment of major stopping places along the route, with the final destination being the Lake Superior region. The metal itself appears throughout Anishinaabe ceremonial and artistic traditions. Pieces of copper are used in Midewiwin, Grand Medicine Lodge ceremonies, and the Lake Superior copper deposits have long been recognised within those traditions as places of spiritual significance. How does this oral history relate to the archaeological record of the old copper complex? The honest answer is that it is complicated. The dates that some of the old copper complex archaeology produces, going back 9,000 years, are older than the dates most archaeologists would assign to the establishment of specifically Anishinaabe identity. The Anishinaabe peoples, as a distinct cultural linguistic group, probably crystallized as such over the past few thousand years, drawing from earlier populations that lived in the region. The earlier populations, the people of the old copper complex itself, were ancestors of the modern indigenous communities, but not in a one-to-one identity. They were the late Archaic period populations of the Great Lakes region. Some of their cultural traditions, including aspects of their relationship with copper, have been carried forward into the practices of the historical Anishinaabe peoples. Other aspects have been transformed. The relationship between the deep past and the present is one of continuity, but not of identity in any simple sense. What is important to acknowledge is that the indigenous knowledge of the region's copper history is a living tradition, not a memory of something that ended. The places that archaeologists have identified as significant, Ile Royale, the Keweenaw, the Porcupine Mountains, the burial sites at Oconto and elsewhere, are places that the indigenous communities have known about, named, and connected to their own histories long before professional archaeology arrived in the region. The 1990 Native American Graves Protection and Repatriation Act, mentioned earlier, fundamentally changed the relationship between archaeology and indigenous communities in the United States. Excavations that proceed without tribal consultation are no longer accepted practice. Materials excavated from sites that can be associated with specific contemporary tribes are subject to repatriation. The professional archaeological community has, in recent decades, made significant efforts to incorporate indigenous knowledge and perspectives into the interpretation of sites in the Great Lakes region, though, as in many places, the integration is uneven and ongoing. The 2021 designation of the Minong Mining District as a National Historic Landmark was developed with extensive consultation with the Ojibwe communities whose ancestors had mined the copper. The National Park Service's interpretive materials at the site reflect this collaboration. The story being told now is the story of identified peoples whose descendants are present and whose knowledge is part of the record. It is no longer the story of unknown ancient miners. The Keweenaw Bay Indian community, in 1991, formally requested the repatriation of the Ontonagon boulder from the Smithsonian, on the grounds that it was a sacred object used in Midewiwin purification ceremonies. The Smithsonian denied the request in 2000, ruling that the evidence did not meet the standard for sacred object under NAGPRA. The boulder remains at the National Museum of Natural History behind the scenes, awaiting a new exhibition. The dispute is ongoing. This shift in how the story is being told matters for how we think about the central question of where the copper went. If the people who did the mining were the ancestors of communities who are still present, then the answer to the question, where did the copper go, includes the answer, into the lives of communities who are still here. the ornaments worn by elders, the objects used in ceremonies, the metal that was in some cases melted down by later peoples and reformed. The trade goods that moved through indigenous networks for thousands of years after the peak mining era. It is not all of the copper. It does not close the gap with the highest extraction estimates. But it is part of the answer, and it has often been left out of the popular accounts. The old copper complex was not the work of a vanished race. It was the work of the ancestors of peoples who are still here, who still know the names of the places, who still have their own ways of understanding what happened. That perspective should be part of any honest discussion of the topic. It often isn't. We have spent the last several parts looking at the visible problem. The copper that was extracted, the copper that was found, the gap between the two, the trade networks within North America, the Bronze Age problem across the Atlantic, the contested isotopic evidence, the contested genetic evidence. But underneath all of that visible problem is a deeper question that does not require any transatlantic contact to be valid. A question that the old copper complex raises just by existing, regardless of whether any of the copper ever crossed an ocean. The question is this: what kind of society can organize industrial-scale resource extraction across thousands of square kilometers, sustain it for thousands of years, distribute the product across a continent, and leave no cities, no writing system, no monumental architecture, and no administrative records of any kind? We do not have a good answer to this. The standard model of how complex social organization develops, which dominated archaeological thinking through most of the 20th century, runs something like this. Agriculture comes first. Settled agriculture produces food surpluses. Food surpluses allow specialization. Specialization produces craftspeople, priests, administrators. Specialization plus surplus plus growing population produces cities. Cities require management, which produces hierarchy, which produces writing, which produces records, which produces what we call civilization. Metallurgy, in this model, comes near the end of the sequence. You need cities to support the specialized labor of metal workers, trade networks supported by the urban economy, and political structures to coordinate the long-distance acquisition of ore. All of that, in the standard story, is prerequisite to working metal at scale. In this model, hunter-gatherers, who have no agriculture, no settlements, no surplus, no specialization, and no cities, are at the bottom of the developmental ladder. They are not, in this model, supposed to be capable of large-scale, sustained, coordinated, technologically sophisticated industrial extraction. They are not even supposed to be candidates for that kind of activity. The old copper complex inverts the model completely. It is metallurgy first. Industrial extraction comes next, with the trade network growing out of that. The agriculture, the cities, the writing, none of those things appear. They are not part of the package. They are not what made the old copper complex work. The old copper complex worked without them. This is not a small problem for the standard model. It is a fundamental problem. It suggests that the developmental ladder, with its assumed sequence from hunter-gatherer to farmer to urbanite to industrialist, is not really a ladder at all. It is a possibility space. Different societies can develop different combinations of complexity in different orders, depending on their environment, their resources, and the particular paths that their accumulated knowledge takes. The Lake Superior copper region had a specific environment. It had copper in pure form, in extraordinary quantities, in a relatively accessible location. The people who lived in that environment built a society that responded to those conditions. They did not need agriculture, cities, or writing to do it. They had what they needed: knowledge of the rock, organization of seasonal labor, networks of distribution, and they used what they had. For a long time, the response of mainstream archaeology to this challenge was to minimize it, to describe the old copper complex as a curious anomaly, to classify the technology as incipient or proto-metallurgy, as if cold-working pure copper was not real metallurgy but only a kind of trial run, to treat the trade network as smaller and simpler than it actually was, to treat the people who built the network as more primitive than the evidence supported. That response has been eroding. The newer generation of archaeologists working on the old copper complex has been pushing back against the minimization. The radiocarbon dates have been pushed back. The geographic extent of the trade network has been documented more comprehensively. The technological sophistication of the copper working has been more carefully analysed. The narrative has been shifting gradually toward an acknowledgement that what happened in the Lake Superior region during the late Archaic was not a minor sideshow to the main story of human civilization. It was, on its own terms, a major development, one that does not fit the standard sequence, one that we have not yet fully understood. In recent decades, scholarship has increasingly explored frameworks for understanding what might be called alternative pathways to complexity. The idea, broadly, is that human societies can develop along multiple complexity pathways, including some that do not run through cities and writing. The thinking goes, there can be sophisticated, large-scale, technologically advanced cultures that look very different from the Sumerian or Egyptian model, and that, if you do not know what you're looking at, can be mistaken for something simpler than they actually are. The Old Copper Complex may be one of the clearest examples of this in the archaeological record. It is not the only one. There are arguments to be made about the pre-Columbian populations of the Amazon basin, about certain Pacific cultures, about parts of pre-Han China, about Bronze Age steppe societies. But the Old Copper Complex is in some ways the most striking, because the technology is so unambiguously sophisticated, the trade networks so well documented, and the absence of the standard markers of civilization so complete. We are still figuring out how to describe what kind of society this was. The vocabulary we inherited from 19th and 20th century archaeology was developed to describe civilizations that grew up around the Mediterranean and the Near East. It is not always a good fit for what the Old Copper Complex did. We are, in real time, having to invent new categories to think about it. This is the part of the story that I find genuinely thrilling. The speculation about transatlantic trade and the contested isotope studies are interesting, but what really arrests me is the plain fact, in front of our eyes, of a society that did something we did not think any society like it was capable of doing, and did it for 6,000 years, and then walked back from it. What we can say has been lost when their heaviest activity ended is more than the copper. It is also a way of organising collective effort, a way of getting very difficult, very large-scale things done without any of the apparatus that we have come to assume is necessary. That knowledge, how to do that, appears to have softened and changed with them. Whatever the mechanism, we have never quite figured out how to replicate it in the form they had. The Old Copper Complex did something we still cannot fully explain. They did it without anything we now consider essential, and they did it for longer than any modern industrial system has yet survived. That is the question underneath the question. And it is the question that, in the end, may be more important than the question of where the copper went. The investigation is not over, far from it. In some ways, the most interesting period of research on the Lake Superior copper region is happening right now. In the past 15 years, several developments have changed what is possible. The Pompeani team's lake sediment studies, which I have referenced repeatedly throughout this script, were not even technically feasible until refined methods for measuring trace metal concentrations in lake cores became available in the early 2000s. The work continues. Each new sediment core from each new lake adds detail to the picture of when the mining was occurring and how intense it was. The 2022 Val et al. Study on Lily Lake and Pond 2 was an extension of the original research, and there is more in progress. The technique itself is being refined. New isotopic methods can now distinguish, with some confidence, between different sources of copper in artifact samples. The methods that would be needed to settle, definitively, the question of whether Lake Superior native copper appears in Bronze Age European artifacts are improving year by year. A comprehensive, well-funded, methodologically rigorous study of Bronze Age copper provenance, including a clean signature for Lake Superior native copper as a baseline, has not yet been carried out, but it is closer to being feasible than it has ever been. The 2021 designation of the Minong Mining District as a National Historic Landmark created a framework for additional research at one of the most important sites in the region. The National Park Service's Cultural Resources Management Plan identified specific archaeological priorities for further work on Isle Royale. Indigenous consultation is now a standard part of the planning process. The collaboration between professional archaeologists and the Ojibwe communities whose ancestors mined the island is producing new questions, new methods, and new interpretations. Digital tools, LIDAR mapping, remote sensing, machine learning analysis of geographic data are being applied to the mining region to identify previously undocumented pits and sites. The total inventory of ancient excavations may be significantly larger than the 5,000-plus figure currently used. As more pits are identified, the total extraction estimates may need to be revised. There is also the slow, painstaking work of re-examining 19th century records. Many of the mining engineers and amateur archaeologists who worked in the region in the 1840s through the 1880s left letters, reports, and diaries that have never been fully analysed by modern researchers. Documents in regional historical societies, in old corporate archives, in the personal papers of geologists like Charles Whittlesey, contain observations that may yet contribute to a more complete picture of what was found, where it was found, and what was done with it. The 19th century record was extensive. It has not been exhaustively studied. The 2018 monograph by John Halsey, Prehistoric Copper Mining in Michigan, the 19th century discovery of ancient diggings in the Keweenaw Peninsula and Isle Royale, published by the Museum of Anthropology at the University of Michigan, is one of the most thorough recent attempts to compile and interpret this body of historical material. What might still be found? A definitive isotopic match, or a definitive lack of match, between Lake Superior native copper and Bronze Age Mediterranean artefacts. This is the most direct path to settling the transatlantic trade hypothesis. The science is doable. The political and logistical barriers are real, but not insurmountable. The study could happen. It has not yet. A genuine ancient transoceanic artefact, if any Bronze Age object securely dated from a credible context, with no possibility of modern contamination, were ever recovered from a North American archaeological site, the conversation would change dramatically. Conversely, if a copper artefact of unambiguous Lake Superior origin were recovered from a securely dated Bronze Age European context, the same would apply. Neither has been recovered in any conclusive way to date. The search continues. Better paleoclimate data for the Great Lakes region during the relevant period. The connection between climate stress and the changes in mining activity needs to be more fully understood. Better climate proxies, from cave speleothems, from pollen sequences, from ice cores, are continually refining the picture of regional environmental conditions during the late Archaic. More complete genetic studies of ancient DNA from the cemeteries of the Old Copper Complex period. With tribal consultation and appropriate respect for indigenous concerns about ancestral remains, careful aDNA analysis could clarify the relationships between the various late Archaic populations of the Great Lakes region and modern indigenous communities. It could also potentially clarify questions about the timing and origins of haplogroup X in the region. The combination of all of this, better dating, better isotopes, better climate data, better genetics, better surveys of the mining sites themselves, means that we will know much more in 20 years than we know now. Some of the questions we have been wrestling with will probably be resolved. Some new questions will probably emerge. The picture will become more complete. It will also, almost certainly, become more complicated. What it will probably not do is become simpler. The Old Copper Complex was not a simple thing. The trade network it sustained was not a simple thing. The relationship between the Lake Superior region and the rest of the ancient world is not going to turn out to be a simple thing. What we can do is keep asking better questions, doing better work, and being honest about what we know and what we do not know. The rock is still there, the pits are still there. The hammerstones are still stacked beside the entrances. The investigation has another century at least ahead of it. It is worth, before we close, doing one thing we have not yet done. It is worth placing the Lake Superior operation directly alongside the famous ancient mining centres of the rest of the world and seeing, in plain comparative terms, what is actually unusual about it. Take Cyprus, the most famous copper producer of the ancient Mediterranean. The major Cypriot operations got underway around the 3rd millennium BC. By the late Bronze Age, around 1400 BC, the Troodos Mountains were producing enough copper to make the island the dominant supplier of the entire eastern Mediterranean economy. The trade was institutional. It was managed by palace economies. The kings of Al-Ashir, as Cyprus was known to its trading partners, correspond in cuneiform tablets recovered from sites including Amarna in Egypt. The Cypriot operations smelted their ore. They cast copper into standardized ingots. The oxhide ingot is the iconic form, a flat slab roughly the shape of a stretched animal hide designed to be carried by 2 people. Those ingots have been recovered from shipwrecks across the eastern Mediterranean. The Alubaran wreck alone yielded approximately 10 tons of Cypriot copper. The Cape Gelidonia wreck, dated about a century later to around 1200 BC, yielded a more modest cargo of roughly 1 ton of copper ingots. But its discovery and excavation in 1960, led by George Bass of the Institute of Nautical Archaeology, transformed our understanding of how this Bronze Age trade actually worked. It was, in fact, the first scientific underwater shipwreck excavation in archaeological history. Cyprus is significant. Cyprus is well documented. The duration of major Cypriot copper production, from beginning to peak to decline, was roughly 2,000 years. The earliest activity in the Lake Superior region predates the major Cypriot operations by some thousands of years. The full duration of intensive old copper complex activity, on the lake sediment evidence, was several times longer than the duration of major Cypriot production. And it did all of this without smelting, without palace economies, without writing, and without cuneiform correspondence with neighbouring kingdoms. Take the Laurion in Greece. Best known as the source of the silver wealth of classical Athens, the Laurion was also a producer of copper, and isotopic studies suggest it supplied a significant share of copper to the late Bronze Age Aegean. The galleries and tunnels are still impressive when you visit them today. The labour was, infamously, often slave labour in the classical period. Athens used large numbers of enslaved workers in the Laurion mines, in conditions that ancient writers described as harsh. The Lake Superior operation, by contrast, shows none of the archaeological signatures of forced labour. Based on what we know about the sites, we can infer the system was structurally different. There are no fortified enclosures designed to contain workers, no evidence of mass burial pits of the kind that characterise the worst slave-driven extraction economies, no debris of guard posts or processing barracks. The seasonal camp pattern suggests the miners came voluntarily, they came seasonally. They appear to have been part of communities that had a relationship with the work, not victims of a system that compelled it. Whatever produced their output, it does not appear to have been the kind of coercion that produced the Laurion output. Take the Iberian Peninsula, where the Tartessian copper deposits and later Roman operations at Rio Tinto produced enormous quantities of copper for the Mediterranean and the early Roman world. Rio Tinto, in particular, became one of the largest mining operations in the ancient world, with vast slag heaps that still mark the country around them. The Roman operation employed an enormous workforce. It used water-powered devices for ore processing. It was, in its later phase, recognisably an industrial-scale enterprise. The Lake Superior operation produced metal over a longer total period, with no water-powered machinery, no Roman engineering tradition, no industrial workforce in the modern sense. It produced this output using stone hammers, fire and patience. Take the Sinai mines, which the Egyptian pharaohs worked for copper and turquoise for thousands of years. The Sinai operations are documented in inscriptions on the rock walls of the wadis where the workings took place. Egyptian officials left their names, workers carved their grievances. The mining was state-organised. It was run by appointed administrators. It was in many ways a model for what state-managed resource extraction looked like in the ancient world. The Lake Superior operation left no inscriptions, no names, no administrative records. What is the point of these comparisons? The point is that the Lake Superior operation was structurally different from every other major mining tradition in the ancient world. The dates are early, the scale is large, the duration is long. All of that is remarkable. But the deeper anomaly is the organisation. It produced significant output without the institutional apparatus that every other comparable tradition required. It sustained itself without the state-level organisation that every other comparable tradition depended on. It operated for thousands of years on a model that we still do not fully understand because nobody else seems to have used the same model anywhere else at that scale. This is what makes it genuinely anomalous in the global archaeological record. The dates are remarkable, the scale is remarkable, but the fundamental organisation is what cannot be matched. The fact that a culture without writing and without cities was for many centuries producing metal at a volume that the rest of the world's most sophisticated state economies would later match only with enormous administrative effort. You can see why the standard story of how civilizations develop has had trouble accommodating it. You can see why mainstream archaeology for a long time preferred to treat it as a minor curiosity rather than a fundamental challenge. The challenge is real. The accommodation is still being worked out. When we ask what kind of society could have done what the old copper complex did, the honest answer is that we are still inventing the vocabulary to describe such a society. The Mediterranean-derived language we use, civilization, state, hierarchy, kingdom, does not quite fit. The dismissive language we have used for hunter-gatherers, simple, primitive, undeveloped, fits even less. The old copper complex is in a category of its own. We have not finished thinking about what that category is. That, finally, is what we should take away from the comparison. Lake Superior was not simply a North American version of what Cyprus did, or what the Laurion did, or what Rio Tinto did. It was something else, older, different, more mysterious, and, in some of the most important ways, as impressive as any of them. The people who built it did not write down what they thought they were doing. We have to figure it out from the evidence they left in the rock. It is going to take us a while longer. In the mid-20th century, a photographer working for the National Park Service walked up onto Minong Ridge on Isle Royale. He had a job to do. The Park Service was documenting cultural resources, building a record of what was there for future generations. He took photographs. One of them showed a poor rock pile beside one of the ancient mining pits. On top of the poor rock, stacked the way someone had stacked them a long time ago, were hammerstones. Stone tools of the kind we have been talking about for the last 2 hours, sitting where they had been left. Photographs of this kind are still in the NPS archives. The same hammerstones are still in the same place today. Every summer, for thousands of years, people came across the cold water to that island. They came in canoes and in small groups. They knew which rocks held copper, where the easier veins were, where the harder ones were. They built their fires. They cracked the rock. They worked. Some of the metal went back across the water with them. Some of it stayed in the ground, in pieces too large to move. Their hammers got stacked beside the pits, the way you leave your tools beside the workbench at the end of a long day, expecting to come back to them in the morning. They were going to come back in the morning. They had been coming back in the morning for many generations. And then, mostly, they did not come back. What happened? We do not know. Maybe they were displaced. Maybe they died. Maybe their descendants simply found other ways to live and other places to be. What they called themselves has not survived. Neither has their language. Whatever they thought about when they sat by their fires at night watching the rock turn red, those thoughts went with them. But we do know what they did, how they did it, and roughly when. We know they were good at it. We know they were patient. And we know that what they were part of lasted longer than any modern industrial economy has yet endured. What we do not fully know, on the higher estimates of total extraction, is where all of the copper went. That question, between what was taken out of the ground and what we have been able to find again, is one of the longest-standing open questions in the archaeology of the Americas. It has been sitting there since the 19th century. It has not gone away. The accumulating research has narrowed some aspects of it and deepened others. The honest position today is that we still do not have a complete account. Maybe some of it is still in the ground in places we have not dug. Some of it might have been recycled into objects we cannot trace. The total extraction estimates may need to come down. Some of the copper may have travelled farther than anyone has yet been able to prove. The most likely answer is that several of those are partial answers, and the full picture is some mixture of all of them, along with other factors we have not even thought of yet. The instruments that could give us a clearer answer exist. The comprehensive isotopic survey of Bronze Age copper artifacts, using a well-characterized Lake Superior baseline, is technically feasible. It has not been done. The reasons it has not been done are partly logistical, partly political, partly a question of whose research priorities get funded. But it could be done, it might yet be. In the meantime, the rock keeps remembering, the pits keep being pits, and the hammerstones keep being hammerstones, and the sediment of the lakes keeps holding its record of pollution layers year by year in mud that has not been disturbed since the people who made the smoke walked away. The copper that is still in the rock is still in the rock. The copper that was taken out of the rock is somewhere, maybe in a buried site in Tennessee, maybe in a private collection in a basement in Iowa, maybe, and this remains an open question, in a bronze ingot at the bottom of the Aegean that nobody has thought to test against a Lake Superior comparison sample, maybe in 1,000 places, maybe in only a few. One of the oldest known large-scale mining operations in the history of the human species has not been fully explained. The people who built it have not been forgotten by their descendants. They have, perhaps, been underestimated by the historical narrative that grew up in the universities of distant countries, where the standard story of how civilizations develop was written by people who had never seen Isle Royale or walked the shores of the Keweenaw. What they left behind, sitting at the bottom of those pits, was their tools and their food, and their wedges of split wood, and their fragments of chipped copper. They also left a question that has outlived empires. The hammerstones are still there, the pits are still there, the water is still cold, and somewhere, in the ground, in a museum, in a Bronze Age tomb, in a forest nobody has yet walked through, the rest of the copper, whatever its true total was, is still waiting to be accounted for. That is where the story ends, for now. The investigation continues.